Okay, I went to McMaster just to take a quick look at what they were doing with the splined rotary shaft. This is kind of some spendy stock, so I'm still thinking for the height that we're at. But their geometry doesn't really show the radiuses, so I can kind of resolve that. There still has to be clearances, and what I was really looking for was a pulley or a drive unit that had this spline in it to see what it was. But we'll let that one go because I'll note it as an investigation for later. All right, so the post, which is going to be for the handle, has a 3/8 on one end, quarter 20 on the other end. Could pretty much go either way with the extrusion. We'll go ahead and close that, or the revolve. I think we'll probably just go with the revolve so that we end up with all of that geometry. So sketch, center line. Anytime we're doing symmetry or revolve, I'm going to go horizontal this time. Horizontal, infinite length for construction, or making it a center line. And then usually just get out of that, go back in, and we want to draw the rough shape. And I am putting this kind of on the center point again, midpoint again. So let's go into the select. We'll make that our midpoint. What do we have? Quarter inch and 3/8, so it's not exactly going to be the midpoint, but could have just as easily put it on one of the ends too. But it's what you see when you see it. So 0.25 by 0.38. I'm not going to worry about the fractionals on the depths here, and because of the way this is done, and because it's a handle, we're not going to end up with a full thread in any way. It's going to having to terminate up against that shoulder. Usually would put a relief in there. As short and as much as we have for the pitch, there's not a whole lot of room in the thickness of the tool or the die. Makes it a little bit of a challenge there. So we'll probably just end up putting a relief on the other end. So let's see, this is going to be the 0.375. I do want to carry that out to its decimal places, and 0.25. All right, and then we had a note. Whoop. Let's cancel that, and we'll go escape to get out of the diametral. Go to 3 inches. That looks a little bit better. Features, revolve, 360 degrees. And then 3/8 quarter 20 just to double check. And we're going to look at the cosmetic threads. So tools and all the way down to, insert all the way down to annotations. Or I can come up and type in cosmetic thread. And we're going to pick the leading edge. This is going to be an ANSI inch, 3/8. We can go up to next. And I usually uncheck the show type because it puts in a note, not really the designation on the thread. So let's maybe add the I to get back into that. And this one finds the quarter 20 up to next. We have the leading edge selected. And we go ahead and put that in. Any chamfers, any reliefs? Nope, doesn't look like I missed anything. So we kind of blew through that one after the last two issues. So post and save. Let's see what's next on in the sequence. All right, so we have the link. And then this is the other side, the 3/16 by 1/8 by quarter of an inch. So we'll do a new part inch, We can go to the front plane, open up our sketch. This is going to be the straight slot, or in the case of it being external, we would go with the oblong. Alright, so I'm going to place those, and once again the straight slot would give me similar geometry. The center point just allowed me to pick the origin and come straight out to the dimension. So our center to center is 4.5 and a radius of 0.75 on each end, so we'll go with that. That one's going to be a 1/4-20, so I'd just as soon use the whole wizard. Not sure that I'm going to end up with the same geometry, so this is a good case to go ahead and make those separate features. And the 0.25 will go into the whole wizard. And we're ANSI inch, making sure that I selected the thread, straight tap. And we're going to scroll back to the 1/4-20. And this should be an up to next, and its position will be at the center. And so dragging over that edge or kind of hovering in that area will usually give you the center. And we'll go ahead and accept it. Alright, so on this end, we'll open up a sketch. And again, staying with the contour and region. Now our center rectangle, if we go that route, and set the 0.25, then this was listed as 0.13. So if we're going to cut that out and make that geometry, center point and that one. Oh, I haven't set the diameter, so this will need just a bit of clearance, but we'll go line to line, 750. And when I go into the features, extrude cut, if we pick that, and we pick that, then I should be able to do a through all. So in this case, I got the two contours. We're going to see what that generates. Make sure it generates the shaft relief and the keyway. So we'll save that as the link. All right, let's see the handle. All right, so the ball for the handle, and then this was saying the 3/8/16 side. I would probably put a generous, and they only called that out 1/2 inch deep. I'd probably go a little bit more and put a generous chamfer so that it doesn't contact this where it can contact that shoulder and doesn't bottom on the thread. So file new, front plane, sketch. We can do this a couple of ways. Don't really know what the flat's going to look like. So they gave it the 0.63. So we'll have to generate that geometry. Let's see, we'll draw it in the same orientation. So horizontal, infinite length, center line. And I need a line to start. And then probably making the choice, I know that the center arc is going to be somewhere, so we could either go 3-point or center point. So if I go center point, that doesn't look too bad. All right, and the radius is 1.5. No, diameter is 1.5, so we're back at 0.75. And from the center, and double check and make sure that's the center of the arc to there, 0.63. Right, and then we can, now that we know where that center point is, I can bring it back to the origin. Because this will be a revolve, we want to close it off and revolve 360 degrees. All right, and then this is going to get the 3/8/16. So interestingly enough, looking at the loading on this, I would want to bring up the point that the quarter 20, while strong, because these are going to be machined threads, there is a stress riser that is a point of failure. That the quarter inch on the link side, that's kind of where we're pushing. That would think that I would want the quarter inch over here. Because if I was going to break something, break the ball off of the end of the handle and not the whole handle off of the link. But that's just kind of thinking through the process and asking the questions as we go. So not going to be an up to next. I did get the 3/16. They gave us a ½ inch, so let's go ½ inch on the thread depth, and that goes up to 0.68. I'm going to give it a little extra. Well, we've got more room than not, so I'm going to give it 0.81. And then the position goes in. So what I want to end up with is a situation where I have plenty of thread. Let's get over to, oh, that was the front. Let's go over to the wireframe. All right, so I have the ½ inch of thread. I have room for the tap. I have all of this, the geometry. And we need 3/8 of that to go into the post and a little bit extra if we need it. Now the other thought, or the other maybe easier manufacturing process, would be to put a set screw in and have it bottom on the post, and that would be a drill and tap as opposed to the drill and running a die or doing a single point thread on that geometry, and then a, say, 1 inch or a 3/4 inch set screw. You would run it in until it bottoms, even put some Loctite on it, and then when this threads on to the set screw, it kind of achieves the same function, but it's an alternative method of assembling the two and maybe reducing the costs. All right, we should be getting down to making a bearing selection. So that got me to the end of my parts. So the ball, the post, the link, and the support. So like I said, I made those guys pretty complicated. Let's talk about the bearing selection, and that should put us in pretty good shape to go make make an assembly. All right, I would still like to find a mating part for this spline and justifying, because usually we'd just put a D-shaped flat, very similar, that we could run a set screw, pulley screw. Even the spline timing pieces would come back to that. All right, so let's go to bearings, and like I said, the ball bearing is just, to me, seems a complete overkill. We'll see why here in a second. I'm going to pull the support back up. I'll go ahead and close that, open that. All right, so we'll double check the depth. I could pull these off of the print, so that was the 11/16, but going directly to the model, whatever adjustments we need to make, we can go ahead and make. All right, so a permanently lubricated ball bearing has a shield, keeps dust and dirt. High speed and precision are not required. It doesn't look like it's sealed. Precision, probably not so much for a hand crank, as the RPMs go up, the rotating mass goes up. You want to get a better situation. So these ball bearings are open, meaning that they're going to have to be lubricated, they're going to have to be cleaned. High load is going to be wider, bigger. The permanently lubricated and the precision are going to have a plastic shield on them to keep them from. So let's take a look at the light duty, open, sealed. Thinking cost-wise, would want to Yeah, so 3/4 inch shaft, and these are showing 1 5/8 and 3/4. The housing goes up to 2 inch for a 1 inch shaft, and then the height is only 9/16 in that group. So this is going to be a standard standard bearing. All right, so back into the 3/4 inch shaft, 1 5/8 for the shielded, and then a sealed bearing. We go through 1 3/4. All right, and then let's look at the permanently lubricated and sealed. So make sure that I'm getting to the sealed. All right, and then this is the industry call out, industry standard, and not sure which one that pulled, but before I pull this out of the toolbox, assuming that it's in the toolbox, and I'm not finding a BS 292, so maybe we'll do a search for it. I do want to check though, 1 inch shaft, 2 inch long. We do have a 3/4 inch shaft. They're all coming back 1 5/8. So, and the height at the 7/16. All right, so that one's even a little bit, but look at these running speeds: 2100, 1100. What is the loading capacity? Dynamic, static. So the rotating 2100, static 1100, 10,000 RPM. I mean, come on. And we're going to spend, let me stretch this out a little bit, and we're going to spend $31.54 per bearing on these. So if we look at this and I go into the detail, let's see, let's go to the PDF. All right, so the other thing is that this inner race usually needs a little bit of clearance. At the very least, it's the same size as the housing. But if that race ends up rubbing on the support, it's additional heat, it's additional contact wear that we'd have to be concerned with. So I'd really want to do a pocketed relief in there just to make sure. And then so let's back up. I'm going to see what's in the toolbox, because hopefully that will be a standard, and if not, then we'll figure it out from there. All right, the oil embedded sleeve bearings. If I go to a 3/4 inch shaft, and I should have quite a bit of selection here. 3/4 inch shaft, we have 2 inches on the width. If we stayed with the same length, all right, so housing ID 7/8, and what was that? The length of the bearing, even at 1 inch, $3.77. Operating range 1,500 pounds. We're certainly not going to be able to turn 10,000 RPM, but maybe we could get 60 RPM out of it, and we're not going to hand crank 1,500 pounds. So on the cost-effective side, my design for manufacturer says we're going to do a configuration that we can present to the customer and say, you sure you don't want to save somewhere in the neighborhood of $25 a part, because we'll spend your money. Anyway, I digress. So the toolbox item, let's see if the toolbox is loaded. Let's go ahead and add it in now. And let's look at the ANSI inch. Is that going to be power transmission? No. Timing belt. Where are we going to hide those? I know that there are, under bearings, of course. All right, so ball bearings, thrust. Now this is a slightly different standard. So instrument ball bearing, thrust ball bearing. Thrust is usually considered, I want to say, axial. And what we're usually doing with radial, let's see if there's, so needles, needle bearing, thrust roller. Well, let's see what we can find in the instrument ball bearing, and we'll hope for the best. I'm not in an assembly, so that would probably help if we go ahead and start the assembly. So while I'm here, I'm going to go ahead and put in a relief. The race is not going to be that thick, so making that 2-inch, we can do like 1.5 just to start, and it doesn't have to be that deep. Extrude cut, blind, and if you leave that out when you insert, when they actually assemble and insert the bearing, it should be pretty plain whether this is a necessary item. All right, so we're ready to go into the assembly. We'll pick up the bearing discussion then.